If you could just write a basic computer program or implement a simple set of rules, then you don't need machine learning. So when we are using machine learning, it's because we really do not know the answer, or we can't compute it. In this lecture, we are going to look at an alternative and better way of building a logistic regression model in PyTorch. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. The motivation behind doing this is that when we perform the sigmoid, we have to do an exponential operation. The problem with that is that exponentials are numerically unstable due to the fact that they grow very fast with respect to the input. In addition, the log term in the binary cross entropy is also unstable for similar reasons. Well, it turns out that because the binary cross entropy loss has a log in it, it almost cancels out the exponential in some sense. Although we won't go through any derivations in this course, the end result is that if you know you have to do both the sigmoid and then the binary cross entropy loss right after, there is a way to combine them into a single function so that you avoid numerical instability. In particular, you can express the loss only in terms of the activation, which is also called the logit in this case. If you've ever studied statistics, then you may have heard of this term before. Otherwise, don't worry. Basically, the logit is just the input into the logistic function, and the logistic function is just another way of saying the sigmoid function. So in this script, pretty much everything is exactly the same, except in two places. The first place is when we create the model. So before, we used the sequential and combined the linear layer with a sigmoid layer. But in this script, we no longer need the sigmoid since that's included in the cost calculation, and therefore our model goes back to being just a linear model. The output of this model is the logit. Then, when we create the loss function, we use BCE with Logits loss instead of BCE loss like we were earlier. As its name suggests, this function calculates the binary cross entropy loss directly from the logits. As you can see, everything after this is the same as well. So our training loop is the same and we get the same results. One more difference we have to pay attention to is when we make predictions. If you recall, the sigmoid always outputs a number between a 0 and 1, and we interpret that as a probability. So when we want to make a prediction, we simply round those probabilities. Anything greater than 0.5 is a prediction of 1, and anything less than 0.5 is a prediction of 0. But what do our predictions look like now, since the output can again be any number? In this case, we just go back to our geometrical picture. You can also think of what the sigmoid actually does, and if you follow that logic, this should make sense. If you recall, anything on one side of the hyperplane, defined by our model, is positive, and anything on the other side is negative. The sigmoid simply maps all the positive numbers to probabilities greater than 0.5, and similarly, it maps all the negative numbers to probabilities less than 0.5. Thus, it's very easy to make predictions. We simply check if the model output is greater than 0 or less than 0. Anything greater than 0 is considered a 1 prediction, and anything less than 0 is a 0 prediction. Note that we can use the greater than sign directly, even though the greater than sign returns trues and falses. As we discussed earlier, in Python, true is 1 and false is 0. Therefore, we don't need to do any further processing. Once we have our predictions, we can check the model accuracy, and again we can verify that the result is the same. In this lecture, we are going to talk a little bit more in depth about training sets versus validation sets versus test sets. First, let's think about why we would want to split our data up in the first place. As usual, I'm going to return to my dumb as possible picture, which is that machine learning is nothing but a geometry problem. Imagine that all the data I collected in the past looks like this. So I find a line that can discriminate between the two classes of data, and I can conclude that my classifier has pretty good accuracy. Great. But remember, what's the point of building a classifier? It's to use it on unseen data that I want to classify in the future. So what happens when tomorrow's data looks like this? Now all of a sudden, the classifier is no good. In fact, it's terrible. Well, that sucks, because this is actually the data I really care about classifying. I don't care about classifying past data. Why? Because I already know what the answer is, so there's no need to classify those data points anymore. Now you might think this example is a little extreme. Clearly the data we have seen so far in this course did not behave this way. When we get good training accuracy, we tend to get good test accuracy. But in fact, we'll see some data that behaves exactly like this later in the course. Here's another image that should help you understand why we need train and test sets. The problem is overfitting. If you have a complex enough model, you will get very good accuracy on almost any dataset. But you can see here that, although we fit very well to the training data, we have a poor fit on the test data, which in this case is the true function that we are trying to model. This is called overfitting, and it's the opposite of what we want, which is good generalization. There's a trade-off that must happen here. Should you make your model more complex so that your training accuracy is improved? Or should you make your model less complex so that there's a better fit to the test data? The problem is, if your model is not complex enough, then it will perform poorly on both the train and test data. So your job is to find the optimal amount of complexity such that it performs well on the test data. It can't be too complex, but it also must be complex enough. You may also know this as the bias-variance trade-off, although this concept is outside the scope of this course. You're encouraged to check out the in-depth series if you're interested in learning more. So I hope that satisfies your intuition about why we need to have separate data for both training and testing. Now, you may have heard that sometimes people split their data into 3 separate data sets: the train set, the validation set, and the test set. What's the difference? Why is it that sometimes we just have train and test, and sometimes we have train, validation, and test? It's really just semantics. When you have a train and test set only, your test set is more like a validation set. In fact, the words test and validation are pretty much synonymous. They mean the same thing linguistically. What you are doing when you split your data into train and test is you are actually using your test set to validate that your model works on unseen data. So in fact, sometimes when people split their data into 2 parts, they'll call them train and validation sets rather than train and test sets. In this context, the meaning of both is exactly the same. I hope you're not confused. So in what case will we want to distinguish between train, validation, and test? For this, I like to think of Kaggle contests, although it's well known that Kaggle contests are not a good representation of how you will do machine learning in the real world. In fact, there have been multiple instances of cheating on the platform. In any case, the way that Kaggle works is this. You will have some data that Kaggle gives you to train your model on. These are typically labeled as train and test. Importantly, the test set does not come with any labels, so you can't compute your model's performance on the test set by yourself. This is unlike when we split the data into train and test in our class. All you can do with your test set is make predictions and submit them to Kaggle servers. Then, Kaggle will show you your test score, along with the test scores from other participants. They will list these on what is called a leaderboard. This is the true test set, because it's how Kaggle is testing your model. But if that's how Kaggle tests your model, then how will you test your model? This is where the validation set comes into play. Remember, Kaggle, generally speaking, although this is not always the case, will give you just a train and test set. You want to perform well on the test set because if you win, then you'll make some money. So you have to make sure that your model performs well on unseen data, namely this test set for which Kaggle withholds the labels. In order to do that, you have to pretend to evaluate your model on unseen data by splitting the train set that Kaggle gives you into train and validation sets. For this data, you do have all the labels, and so you can calculate both the train and validation accuracy. Sometimes, although this isn't usually done in deep learning, you will split your data randomly into train and validation sets multiple times. We call this cross-validation. Here's the basic idea. Let's suppose you split your training data into 5 parts. Then you'll do a loop which runs 5 times. On each iteration of the loop, you'll consider 4 of the parts to be your train set and the remaining part to be your validation set. On each iteration, you will train a new model on the current train set and evaluate the model on the current validation set. When you're done, you'll have 5 different validation scores, and from this, you can calculate the mean, variance, and so forth to get some statistical measure of how well your model might perform on unseen data. The reason this isn't used for deep learning is that the datasets are usually so large and training takes so long that the variance is pretty small, and just one validation set should give you a pretty good idea of your model's performance. There is a small caveat to the leaderboard. In fact, there are 2 leaderboards, the public leaderboard and the private leaderboard. The public leaderboard is where your score on the test set is shown. The private leaderboard uses yet another dataset, and this is the one on which the winner of the contest is selected. This is of course to prevent overfitting to the public leaderboard test set. The public leaderboard allows you to submit a solution multiple times, so you have some chance of overfitting to it. On the other hand, you only know your private leaderboard placement once, at the end of the contest. So in fact, to confuse you even more, now there is not just the train set, the validation set, and the test set, but there is yet another test set. Of course, Kaggle is not the real world. In the real world, your test set is the set of data for which you really want the answer, but you can't produce using non-machine learning techniques. If you could just write a basic computer program or implement a simple set of rules, then you don't need machine learning. So when we are using machine learning, it's because we really do not know the answer, or we can't compute it practically. Some basic examples of this are fraud detection, spam filtering, or object detection. We really want these to work on data that we haven't seen before, but it's clear that we can't do that work manually. The next question I want to answer is, what is the validation set even for? You might be thinking, sure, I can evaluate the model to get some idea of how it will perform on unseen data, but then what? What do I do with that result? How is it actionable? Recall that in machine learning, we have a lot of choices. We call these choices hyperparameters. For example, in gradient descent, we have to choose the learning rate. We can't learn the learning rate. As you learn more about different variants of gradient descent, you will have to choose between those variants, and then among those variants, there are yet more choices of hyperparameters. If you have a lot of input features, you might want to choose just a subset of the features so that the model can learn from the important features rather than just the noise. You also have to choose between different model architectures. After you learn about basic linear models, you'll learn about ANNs, CNNs, RNNs, and so forth. You'll have to choose the number of layers in a network and the number of units in a layer. You'll also have to choose activation functions. There are so many choices, you will feel overwhelmed. Unfortunately, it's not possible to choose these hyperparameters automatically. You can't just do gradient descent on model architectures. At this stage, your approach amounts to just trial and error. And so, how do you evaluate each of these different choices? The answer is by using the validation set. Typically, you will pick the model that gives you the highest validation score, and that will be the model that you use on your test data, whether that's a Kaggle contest or pushing your model to production. So in this short lecture, I want to tell you about my suggestion box. The idea behind this is analogous to the kind of suggestion box you would find at a restaurant. You can write down your thoughts and leave them for the owner to look at to give them feedback so that they can improve your dining experience. In order to share your thoughts with me in my suggestion box, please go to lazyprogrammer.me/suggestions. Here you will find a simple form where you can tell me anything you like. I have a few suggested fields, but none of them are required. However, they would be helpful for me to know. For example, tell me your background. I think someone coming from a background in marketing is going to have very different feedback compared to someone coming from a PhD in physics. Tell me what course you are taking so I have some idea of what you are talking about. Obviously, the more specific you are, the better I can help you. Tell me how difficult you thought the course was. Was it too easy? Was it too hard? Tell me if there was something I neglected to explain. For example, was there some word that I used that you have never heard of? Was there Python code that you haven't seen before? Tell me what you thought was missing from the course, even if it was just something small, like you missed explaining this line of code. Were you looking for an algorithm that wasn't included? This is helpful for me, but it's also helpful for you because many times, students are looking for an algorithm or an explanation in the wrong course. So I can say, actually, I teach that algorithm or I explain that thing in such and such course, and this isn't the right course, so have a look over there. Are there any topics you want to request that were not included in this course? For example, maybe you signed up for a deep learning course, and you were looking for CNNs, but the course didn't have CNNs in it. Let me know. Finally, let me know your suggestions for future courses. If there's a particular topic you want me to teach that I don't yet have a course about, such as gradient boosting or transformers or even quantum mechanics, let me know. Finally, there is a big text box for any comment you want to write. You can write anything in this box and make it as long as you want. In fact, the longer the better. If you think I talk too slow or I talk too fast, let me know. If you think my prerequisite instructions aren't fair, let me know. I want you to be as specific and as detailed as possible. A lot of the time people give me comments that I can't really act on, which is unfortunate. And this is often because they are too generic and not specific enough. Tell me exactly what lecture and exactly what timestamp you're referring to. If you want to refer to a question on the Q&A, include a link. Be very specific and give me concrete examples so that I know exactly how to act on the information you've given me. Thanks for listening, and I'll see you in the next lecture.